Hello, you beautiful people. So this is part 2 of our lecture 4a. Yes, in the last lecture I showed you how to implement DWSim, how to implement the kinetics in DWSim, and then we had a small reactor. But what I want you to show, and this is the new process layout. And for this, we need a new unit operation, and this is the heat exchanger. So, okay, before we go to the reactor sizing and your homework, let's talk about the heat exchanger. Okay, I use the same flow sheet here. Then with this, I already have my flows and so on. So yes, what we can do is we go to exchangers, and then you will find here the heat exchanger. Okay, and the heat exchanger is operating with four connections. So if you open it, then you can see inlet stream 1, outlet stream 1. So we create it again. So this is like a heat exchanger that you know from heat and mass transfer, and you already have, whoops, create and connect and create and connect. Okay. Now we can rename it. Let's call it in 1. This is out 1. This would be in 2. And this would be out 2. Okay. Yeah, and for this, maybe let's assume this should be, so let's clear it all, and then we say, okay, maybe this is just methane, pure methane. Enter, and of course accept changes. And we want to have this at a high temperature, so 300 degrees Celsius, for example. So basically this doesn't matter much. And here we can say, okay, this might be pure nitrogen. So it's clear all, then it's 1 and accept changes. And this can be cold, okay. And then in the heat exchanger, there are, you can say, okay, flow direction, counter current. So normally you are using counter current since it's more efficient to use counter current flows. Okay, and then let's say this should be 300 degrees Celsius. And so right now here you just have somehow you have a global heat transfer coefficient. I don't know, maybe let's change this to 50. And the heat exchange area could be 10 square meters. And then you would get something like here, outlet temperature and outlet temperature there. So this should be one option how you can define your heat exchanger. But sometimes it's more convenient to say, okay, I want to cool down my flow 1. So my methane, I want to cool it down to 150 degrees Celsius. So, and then you basically DWSim shall give you the outlet temperature of your nitrogen. And this can be done if you say, okay, what shall be calculated? Your cold fluid outlet temperature shall be calculated. That's why your hot fluid outlet temperature you can specify. So this would be 150 degrees Celsius. And then you could have, whoops. Okay, now we have a temperature cross because the heat capacities are so different. That's why I just have to, let's say here, what's how much? Let's say 10,000 kilograms per hour whatsoever. Okay, now it seems to work. Okay, at least you get a warning when you are doing something that it's not allowed. If you have a temperature cross, then at least you get a warning. But yeah. Okay, so with this, you can say 300 degrees in, 150 degrees out, and then you will see, okay, my nitrogen leaves the heat exchanger with a temperature of 173.935 degrees Celsius. Okay, you can also do it the other way around if you want to say, okay, my hot fluid temperature shall be calculated, and you want to heat up your cold fluid. You want to heat it up to, let's say, 100 degrees Celsius. Whoops. Then you will find, okay, this is 228 degrees Celsius for my methane. And that's how you can play around. As an additional information, you can also specify the heat transfer coefficient, and the heat exchange area is calculated, I think. Or is it the other way around? Maybe if you say 20 here. Yes. So it's always a pair. So if you look at the equation, then it's always in German it's K times A. So the global heat transfer coefficient times the area. So they are always a pair. And if you say, okay, I want a lower, I want to have a lower heat exchange area, then somehow I have to make sure that my heat transfer coefficient is increased. Okay, so basically that's what you can do here. So where's the difference between outlet temperatures and outlet temperatures UA? Okay. Yeah, basically that's it. That's what I use the most. And for your homework, it might be somehow helpful that you have the heat exchanger here, where you can specify a certain outlet temperature of one flow, and then you will know what's the other outlet temperature of your heat exchanger. And you have to always make sure, if you have something like an internal heat exchange, then you might have some, then you need a where is it? Then you need a recycle block for your material stream. Okay, so much for the heat exchanger. Now let's go back to our presentation and to our process layout. If you remember, I showed you this graph. And here I just said, okay, this is like a black box. We have here our reactor. It should operate at 450 degrees Celsius and 300 bars. And from the things I told you so far, you might know that it's not possible to have a uniform temperature inside the reactor. So it will be something like adiabatic operation in some parts, so you will have temperature change inside the reaction. And yeah, what will we do? What we have is we take our flow here coming from the internal heat exchange after the low temperature ammonia removal, and then we split it up. The major part is preheated up to, I think, 150 degrees Celsius. Then you have an internal heat exchanger again. So HEX is a kind of a common abbreviation for heat exchanger. And then the major part you send to the inlet of your reactor. Then you have here a catalyst bed, so this should be this should symbolize your catalyst loading. And then your first segment of the plug flow reactor is over. Then you have injection of fresh feed. So this is taken here with like 15 degrees Celsius. One part is sent to yeah, somewhere between the first and the second plug flow reactor. With this, you decrease the conversion, and you also decrease the temperature. Then you have your second part with catalyst. Then again, you have fresh feed here, and then you have your third plug flow reactor, and then you leave the reactor quite hot, and you use this heat for the heat exchanger. And After this, then you produce steam, then you'd have the first stage of internal heat exchange, and so on. Okay, and in the example, I found here some values. So we have the flow 1. This is the fresh feed, but preheated, 150 degrees Celsius. And we have the composition. Flow 2 has the same composition as flow 1. It's just at a lower temperature. So the only difference between this flow and this flow is that here you have the preheating of 150 degrees and here it's 15 degrees. That's the only difference. And your flow leaving the reactor, it has a composition of roughly 17% of ammonia. So here, this is the mole flow in kilomoles per hour. And so watch out, since we are English speaking right now, this comma here is the decimal. It's the, or what is it? The symbol for 1,000. So this is 14,826, 4,996, and so on, 17,000. So in English, dot and colon are exchanged. Okay, and yeah, what's your task? You should build a simulation in DWSim that comes as close as possible to these values. I made a screenshot of my simulation, so I was a little bit lazy. I didn't find fancy names for the material streams, so it's a little bit confusing, but it should look like this. So you start here with the heat exchanger. Here you are coming with the fresh feed. You heat it up to, I think it was 400 degrees Celsius. Then you have your first plug flow reactor. Then you have cold fresh feed, 15 degrees Celsius. You mix it, and then it's, yeah, you have more nitrogen and less ammonia and a lower temperature. You send it to the second plug flow reactor. Then you mix it with the next fresh feed. Then you send it to the plug flow reactor. Then you have the high temperature at the outlet. You send it through the heat exchanger. And basically that's what you have here. Yeah, and yeah, this is how it might look like. The recycle blocks, if you have like one big volume flow, because what I gave you here is the total flow for stream 2. It's in total, it's roughly 5,000 kilomoles per hour, but I don't know how it is splitted between these two injections here. So this is also something that you have to find out. And if you want to do it with a splitter here beforehand, then you might need something like a recycle block so that that DWSim knows the values to calculate it. So for the recycling here, I'm quite sure that you will need a recycling block, otherwise it will not work. And for the recycle blocks, it's useful, or it's important to find useful tolerances. So you will see that here we have high mass flows, and maybe the default value there is not the best, but this you might find out by try and error. Okay, the homework for you is, so every one of you should do the simulation and you should try to come close to the given data. So you will not get a perfect match. It would surprise me if you find it, but try to come as close to these values and yeah, discuss your solution in your group. And since this I cannot do just like a test in email that is corrected automatically, I want you to do it again in your 4 groups. And for every group, you should prepare a document with your results and short remarks. Yeah, some questions. What is the outlet temperature of the last plug flow reactor? Then assume a reasonable overall heat transfer coefficient. What is the corresponding heat exchange area? What is the reactor volume of the 3 plug flow reactors? And here you have to You have to remember in reality, so volume is money. If you say, okay, this is really a big reactor, I need like 1,000 cubic meters, no one will pay for it. So volume is money, so you have to make it as small as possible. What is the split ratio or the mole flows of fresh feed to plug flow 3 and plug flow 2 and plug flow 3? So I want to know these 5,000 kilomoles per hour, how are they distributed? Is it like 1,000 here, 4,000 there, or vice versa, or whatsoever? And yeah, describe briefly your approach to find a solution. So you cannot answer them one after the other, but somehow you have to modify your simulation in a way that, yeah, that somehow you get close to these values. And when your agreement is quite good, then you might answer all the questions. And maybe you can describe in this PDF file, maybe you can describe what you did to find a solution. Okay, basically that's it. Thanks for watching and good luck for your homework.